Welcome back to AIAA Public Talks again. Just a bit of housekeeping before we start with the talk as usual. This talk is organized by AIAA, American Institute of Aeronautics and Astronautics, Sydney section, which is a professional organization that connects aerospace professionals. If you're interested in what we do or you would like to join, please check AIAA.org. Format of the talk tonight is Rounak is going to talk, and then we'll have Q&A questions time. Please do mute yourself during his talk, and any questions send them to me via chat, and then I'll sort through them and ask them at the end. That's fair for everyone. A bit unusual because Rounak is in Japan. If there is an earthquake, he is going to promptly disappear from the screen and hopefully reappear shortly. He will just hide under the table while the tremors go. If there is an issue with his connection, he might drop out. Please stay on the line because he'll try and reconnect as soon as he can. All right, that's it for the housekeeping. I'm going to introduce Rounak now. I'm pretty sure most of you know him already. Born in India, Rounak began his journey in the aerospace world by completing a double degree in aerospace engineering and business management at RMIT in Melbourne. He then continued with a PhD at UNSW in Canberra on planetary reentry and scream jets, and also continued onto his postdoctoral studies in Canberra. And it was involved in many interesting projects, which he will talk about. In 2019, Rounak was awarded Japan Society for the Promotion of Science Postdoctoral Fellowship and is now conducting research at the JAXA Kakuda Space Center in Japan, in Miyake. Rounak loves piano and is an amateur astrophotographer and a massive Lego fan. With that, Rounak, the microphone's yours.
Great. Thank you, Yasha. Can everyone see my screen? Yasha, can you see my screen?
Yeah, your screen's clear.
Thank you, Yash, for the introduction, and good evening, good morning, good afternoon, depending on where you're watching this talk. And thank you for joining me today as I talk about my journey into aerospace research and how I landed up working at one of the largest ground testing facilities in the world for high-speed aerodynamic research at the Japan Aerospace Exploration Agency, or JAXA. I join you from a small town called Tsukinoki, which is roughly on the border of rural and suburban Miyagi in northern Japan. Here's the structure of the presentation, in which I will share with you key elements of my journey that shaped and influenced me to become an aerospace engineer with the goal to pursue a career in space exploration. In the course of this talk, I hope to achieve three main things. One, give you an insight into the various stages of my progression towards becoming a research scientist at JAXA. Two, perhaps motivate some of you, particularly those of you who are thinking about pursuing a career that you're passionate about, or if you've just started your journey, which may or may not be aerospace engineering. And three, to show you that my journey was far from a smooth sail, and that I faced my share of disappointments and failures, but ironically, learned and grew the most as a result of them. I'd also like to mention that this would be the first time I've shared the backstory to my career in a public forum. And for that, I'd like to thank the AIAA Sydney section for presenting me with this unique opportunity to do so. So let's get started. My journey begins in India, where I was born. I was born in a city called Pune, which is located in the western part of India. I hope you can see this. It's shown here in this blue circle. I grew up in a typical middle-class household, with my father being the primary breadwinner and my mother, who paused her career to become a full-time stay-at-home mom to look after my sister and me. The one interesting and probably atypical thing about my family is that we spoke English at home. English is my mother tongue, unlike majority of my school friends back in India. This is because my father and mother come from two different parts of the country and spoke two different languages. Mom's mother tongue is English and dad's is Tamil. I guess at some point they had decided to make English the working language at home. This would, however, prove to be a major strength when we migrated to Australia. My schooling years were split between two schools. St. Joseph's Boys School in Pune, a picture of the quadrangle of the school which is shown over here, and the school where I started my kindergarten up to year 8. And then after that, we moved to another city called Nagpur, which is located in the absolute center of India. And I did my year 8, year 10 in a school called St. Francis de Sales, or SFS. Due to the sheer competitiveness in the Indian education system and very limited number of seats available at top universities, my parents did everything to make sure that my primary focus at school was to excel in my studies. Now, this is not uncommon in the Asian culture, and some of you listening know exactly what I'm talking about. The mantra at home and indeed at school was studies first, everything else second. Naturally, there was a lot of pressure to perform well at school, as was the case for all of my peers. It was just a norm and something you got used to through your years in school. Thankfully, I'm fortunate to have parents who encouraged and supported me to go beyond just my studies and develop other skills such as public speaking, learning music, playing sport, just to name a few. These were welcome distractions from the routine of my academic work and something I looked forward to and enjoyed immensely. These old pictures shown here are a few examples of the extracurricular activities I was involved in during my school days in Pune and Nagpur. I strongly believe all of these experiences not only helped me develop useful skills and habits, but it also taught me to appreciate and enjoy other things in life besides academic work. And for this, I have my parents to thank. When it came to deciding what I wanted to do as a career, I went through two phases. The first one I call the influenced career choice, through the power of suggestion either by my parents, family, or teachers, I'm not entirely sure. As alluded to in these memes, so like shown here, there are 4 main choices you have. You can either become a doctor, a lawyer, an engineer, and if not any of those 3, then just a disgrace to your family. There is a notion in the Indian psyche that there are a handful of career choices that one should choose from in order to be considered successful in life and be respected in society. In my experience, which is probably true even today in many parts of India, a person's worth and status in society are strongly defined by their profession. It defines their identity and how they're treated by others. So naturally, my elders wanted to make sure I fitted the societal mold and suggested that perhaps I should consider becoming a computer engineer because it was the hot new thing at the time. I honestly did not have a clue what it meant to be a computer engineer, but I happily gave that answer to anyone who asked me what I wanted to become as an adult. Now, like a lot of kids of my age, I was a huge fan of sci-fi shows such as Star Trek, for example. And for a young mind, that show did a lot in capturing my imagination of space travel and exploration. However, there were 2 triggering events that made it absolutely clear what I wanted to do as a career. This was the second phase, and I call it the actual career choice. The first event was a meteor shower, specifically the Leonid meteor shower of 2002. The newspapers had reported that there was going to be a spectacular display in the night sky, and so I woke up at the ungodly hour these things tend to occur, and went out and watched what was truly a spectacular celestial event. Now, this may sound a bit cheesy, but that event had triggered a deep emotional and intellectual response to the sense of beauty and mystery of the universe in my young mind. Incidentally, the Japanese have a word to describe such a response. It's called yugen. As you can probably imagine, my mind was bubbling with questions such as, where do these meteorites come from? what are they made of? Why do they glow a certain color as they streak across the sky? And so on. And for a while, I did consider becoming an astrophysicist. This was until the second event in 2003. Before the catastrophe that occurred on February 1st, I was vaguely aware of Dr. Kalpana Chawla, who was the first Indian-born US astronaut. I knew she was an astronaut, but I was not aware of her background and story of how she made it. I remember watching it on the news live as I saw the Space Shuttle Columbia re-entering the Earth's atmosphere, but to everyone's horror, in several bits and pieces. For those of you who are unaware, the shuttle was destroyed during a routine re-entry phase of the mission due to a compromised heat shield that was damaged during liftoff. The entire crew of STS-107 had perished during re-entry, and for a lot of Indians, we had lost our hero. As you can probably imagine, I started to read a lot more about Dr. Chawla and the events leading up to the accident, and as I'm sure a lot of people did at the time. I found out that she had completed a degree in aeronautical engineering, which is a subset of aerospace engineering, and that she was an experienced pilot. This prompted me to have this really crazy and ambitious idea of wanting to continue her legacy of inspiring people to become the best versions of themselves. And I decided I was going to follow in her footsteps towards becoming a mission specialist astronaut. I was going to become an aerospace engineer similar to Dr. Chawla, and combined with the meteor shower event, I was determined to pursue a career in space exploration. Now, although I was a dreamer, I still am a realist, and I had plans B, C, D, E, and F in the very likely event that I did not become an astronaut. And I'm happy to discuss those during question time. A turning point of my journey was my parents' decision to migrate to Australia. The primary motivation for migrating was to provide my sister and me with ample opportunity to succeed within a more forgiving Australian education system. Unlike the Indian education system, a couple of percentage points lower in year 12 or 12th grade did not mean completely eliminating all hope of getting into the course and university of our choice. So my parents made the incredibly brave decision to leave behind decades worth of hard work and toil into building a respectable and comfortable life in India to pursue the possibility for a better one, 7,800 kilometers across the globe in Melbourne, Australia. As with any new beginning, particularly in a new country with a different culture amongst 100 other different new things, there were challenges that we had to all learn to navigate through before life became settled and comfortable. For me, those included adapting to a new culture and environment, getting used to a new school, which was co-ed, unlike the ones I attended in India, and making new friends who were from different ethnic and cultural backgrounds. And I think for me personally, that was both a slightly scary, but also a very exciting time. So both my sister and I were very fortunate to attend a very good public school, McKinnon Secondary College, that had all the opportunities we needed to flourish academically and in other activities of our choosing. And I've listed a few of them on the slide. So having achieved the year 12 or enter score, or the score I required to do aerospace engineering at RMIT University, I began a double degree in aerospace engineering and business management, which lasted for about 5 years or so. Now, unfortunately, the double degree course at the time did not have any space-related courses that I could take, even as an elective subject. This was mainly because the course was designed to ensure that graduates were job ready for jobs mainly available in Australia. At least that's what I believe so. They were mostly in structural engineering and material science for civil and military aircraft. However, that was not really something I was interested in or passionate about. So I had to find other opportunities to keep me motivated and to remain steadfast in my goals. One of these was the RMIT International Industry Experience and Research Program, or RIEP, that made it possible to complete a 7-month internship at the German Aerospace Center, DLR, near Munich in Germany. During my internship, I worked with a team of the Mobile Rocket Base, or MORABA, that are launch providers for scientific payloads on sounding rockets and high altitude balloons. Shown here is an example of a payload launched by Bonaba, the Sharp Edge Flight Experiment number 2, or SHIFEX-2, which was an experiment designed to test a novel thermal protection system for atmospheric re-entry that used multifaceted surfaces built from ceramic-based tiles located on the cone of the payload. It's not too clear in the image, but it was the case. Of the many projects I was involved in, I was fortunate to work on the SHIFEX-2 project, particularly on characterizing the performance of the nozzles, like the one shown over here, the nozzles used on the attitude control system, which is basically a system that fires these jets using nitrogen gas usually to control and correct the orientation of the payload during flight. My internship at DLR was a valuable experience for two main reasons. Number one, I gained first-hand experience in solving problems that were directly related to space technology. And two, I had to learn to live in a new country for the first time by myself with language and cultural barriers. When I got to my final year, I had realized that I did not have any experience in computational fluid dynamics, or CFD, which is basically using a computer to solve a bunch of equations used to model fluid behavior for a specific application. I was determined to gain some experience in CFD before graduating, and it had to be an application that I was interested in. So I picked a CFD-based project that was about modeling hypersonic flows, as it directly related to applications such as planetary re-entry of spacecraft or meteor showers, and also high-speed air-breathing aircraft known as scramjets. Just for those of you who are unaware, the hypersonic flow regime deals with flow speeds that are greater than 5 times the speed of sound, or Mach 5. The aim of the project was to see if a commercial code called ANSYS Fluent could accurately model a phenomenon called shockwave boundary layer interactions for a low Mach number flow. Just very briefly, the shockwave boundary layer interactions are complex flow phenomena that can occur on aircraft traveling at hypersonic speeds. And such interactions, if not understood properly and accounted for in the design, could have detrimental effects, such as structural damage on aircraft surfaces, like the one shown here on the X-15, where the result of shockwave boundary interaction caused thermal damage to the vertical stabilizer of the aircraft. And it could also affect the performance of scramjet engines. Sorry. Now, since I did not have any experience in computational modeling of flows of any kind and little to no understanding of these shockwave boundary layer interactions, I had to adopt a step-by-step approach to first develop a basic competency in modeling simple flows traveling much slower than the speed of sound before advancing to the more complex hypersonic flow problem. Thankfully, I was able to show, after going through that whole process, that the commercial code had limited ability to model flow parameters when compared to the experimental data for the particular flow case I'd chosen. Now, there's only so much you can learn in a single year about a non-trivial topic. However, I had gained an appreciation for CFD, and more importantly, I'd begun to learn the approach to learn to teach myself a completely new topic from scratch. Now, in addition, what I had discovered was that I really enjoyed research, and I wanted to continue down that path. And while the CFD-based project was interesting, I also knew that I did not want to sit in front of a computer performing analysis as my primary research method, but instead work in a lab with actual hardware. Initially, my search for a research topic in hypersonics was limited to Australia and the US, as majority of the interesting projects were available in these countries. However, having weighed my options, I finally decided to do a PhD in Australia. One of the well-known universities in hypersonics research in Australia is the University of Queensland, or UQ. It is where pioneering research in the late 70s to the late 80s put Australia on the map and made it a world leader in hypersonics research. So naturally, it made sense to do my PhD at such an institution. Consequently, I had firmly set my sights on UQ and started applying for PhD positions. Around the same time, I had attended the AIAA Student Paper Conference, which was in Adelaide that year, to present my work for my final year project at RMIT. It was there when I had met this fine gentleman shown here in this picture here, an Air Force officer in the Royal Australian Air Force, flight test engineer Dawson Shuck, who had also attended the conference to present his final year project he had undertaken at the University of New South Wales in Canberra. Dawson's presentation had shown me something I was previously unaware of, that there was and still is hypersonic research being done at a location much closer to Melbourne in Canberra. So I approached Dawson during the conference to talk about his work in Canberra when he mentioned that his research supervisor was actively looking for PhD students. I guess I was so sure that I was going to UQ at the time that I felt I had nothing to lose in passing on my details to Dawson, who introduced me to his supervisor and who would eventually become my PhD supervisor and my boss for my first postdoc, Associate Professor Sean O'Byrne, shown in the picture over here. Here's the picture of Sean, who was a senior lecturer back then, I believe, receiving the prestigious Spitfire Fellowship from the then Governor General Bryce. I show this particular picture because it was the funds from this very fellowship that were used to develop the hardware for my PhD research. So following the conference in Adelaide, Sean had contacted me and told me about all the hypersonics and non-hypersonic space projects offered at UNSW. He was incredibly responsive to all my questions and concerns I had about doing a PhD, whilst on the other hand, I was still waiting to hear back from UQ. So by that point, Sean had adequately convinced me why I should do a PhD at UNSW Canberra. So having thought about it a lot, and after several discussions with friends and family, I made the decision to head over to Canberra, a place that was never on my radar until then, to begin a 4-year or so adventure into PhD research. So Sean had offered 3 to 4 projects to pick from, and I opted for the project. And I'd opted for the project which had in its description supersonic combustion using laser-based and short-duration pulsed plasma ignition. Mouthful, I know. As an over-enthusiastic, naive graduate, I thought I was going to do all of those things. However, after calming down a bit and realizing the sheer enormity of the project, it became obvious that I was going to do only one of those things, namely investigating short-duration pulsed plasmas in a stationary gas using laser diagnostics. For those of you who are unaware, plasmas or electrical discharges are commonly referred to as the 4th state of matter. So you have solids, to which adding energy turns into a liquid, which then turns into a gas with the addition of more energy. Now, if you were to add more energy to the gas in the form of, say, an electric field, you'd begin to strip the atoms and you'd begin to strip the electrons of the atoms and molecules, and then generate an electrically conductive gas that was previously completely neutral and non-conductive, and that's a plasma. A couple of examples is one shown here on the right, which is lightning seen during thunderstorms, which is a type of hot plasma. And on the other side of the temperature scale, you have things like neon signs shown at the bottom over here, which is a type of a colder plasma. So much like my undergraduate final year project, I had absolutely no clue about the things at the start, nothing about laser diagnostics, optics, or plasmas. Add to that, I had very little lab experience. Yes, I did wonder many times if this was completely illogical and just plain stupid. However, with the help and guidance of my supervisor and the experience I gained during my undergraduate project, I approached the problem by breaking it up into smaller, more manageable bits. The first step was to develop competencies in plasma diagnostics, specifically in the laser diagnostic technique called tunable diode laser absorption spectroscopy, or TDLAS. Now, I won't get into the specifics here, other than to say that it is a method by which the properties of a medium, such as a plasma, an absorbing medium, the properties such as temperature and density can be determined without a physical probe being present. So it can be done non-invasively using a laser beam. During my first year, we had a visiting academic, Professor Philip Varghese, shown here on the left, a leading expert in plasma diagnostics from the University of Texas in Austin, and with whom I was fortunate enough to work and learn about the basics of plasmas and laser diagnostics. With his help and Sean's, I was able to set up my first plasma diagnostic experiment. The first experiment involved measuring the temperature and density of excited argon atoms present in this discharge formed here, which is a plasma reactor that is part of a device known as a sputter coater. So a sputter coater is just a device that is used to deposit thin films like metallic films like silver, for example, on a substrate. So here's the glow plasma. It's a type of low pressure argon plasma. Because of the success of the experiment, in addition to presenting the results at a big conference, my supervisor had put in a patent application for the plasma diagnostic technique as a tool to quantify the performance of commercial devices, commercial sputter coaters, which was a completely unexpected outcome of this experiment. The next step was investigating pulse plasmas that last for 100 nanoseconds or 100 billionths of a second. They're referred to as nanosecond duration repetitively pulsed discharges. I know that's quite a mouthful. And so the short form is referred to as NRPD. And why are they important? Well, these discharges have a wide range of applications, from supersonic combustion to sterilization of heat-sensitive surfaces. They're interesting because unlike conventional hot sparks that heat up the channel of gas to very high temperatures, these pulse plasmas are capable of generating excited atoms and molecules that may be used for a particular application without significantly heating up the surrounding gas. And that's the key difference. This is achieved by switching on and then quickly switching off the electric field that prevents it from turning it into a hot spark. These plasmas are underpinned by complex physics, and in order to understand them and thereby control their behavior, it's important to make measurements. So to that end, we developed a very fast detection technique based on absorption spectroscopy to quantify the temperature and density of excited argon atoms that were produced during and after each of these 100 nanosecond pulses. While we unfortunately weren't the first ones to develop such technique, I believe we still hold the record for the fastest measurement using this technique. However, the most important thing to come out of this work was the discovery of a new phenomenon in these discharges that was previously unknown because of the ability to make such fast measurements. So shown here is the plasma reactor that was built out of commercially available parts that I used to conduct my experiments. And on the left is the CAD diagram of the central section of the cell, showing the internal part of it with the two copper plate electrodes between which the plasma was generated. On the left is an example of a low pressure NRPD. And I show this image because this was a result of my curiosity to see what would happen if I slowly pumped out the gas from within the cell while the plasma was still on. And I thought I had discovered something new when I saw these bright, dark, alternating dark and bright bands. But it turns out some guy by the name of Michael Faraday, who is a big deal, by the way, was the first to observe them in the 1930s. Nonetheless, I would like to think I experienced the same emotional response as Faraday when he discovered it for the first time. I was also able to apply my diagnostic technique to investigate a different kind of plasma generated in the MatPi facility at the Australian National University through a grant that was awarded to me by the Australian Institute of Nuclear Science and Engineering, AINSE, which is again another example of an unexpected outcome. Besides spending time in the lab on my research, I also found opportunities to talk about my work or topics within my field at STEM outreach events organized by the AIAA Sydney section, such as at air shows shown here on the right, and at events organized by the university, such as the Young Women in Engineering, or YOWE. If you're unaware, STEM stands for Science, Technology, Engineering, and Maths. One of the highlights during my PhD was representing UNSW Canberra at the 3-minute thesis competition in Sydney, and then later being invited by Robin Williams, not the actor, on the science show on ABC National Radio to broadcast the talk I gave at the competition. In addition to the sheer pleasure of sharing with people the excitement of aerospace research or just general science-based topics, I participated in these events because it provided me with the opportunity to practice and improve my science communication skills, as well as highlight areas of my understanding on a given subject that needed further development and further work. It is also one of the reasons why I have signed up to talk at local schools about science and my research here in Japan. Now I want to spend some time on this slide to talk about the less glamorous part, yet probably some of the most valuable experiences gained during my PhD candidature. And in comparison to the challenges faced in my undergraduate degree, my PhD journey was a very steep learning curve that involved a lot of stumbling before things started to work themselves out. One of the first things I learned during the first 2 years of my PhD is that as a researcher, you're very unlikely to make a major breakthrough in your field. Not impossible, but improbable. I think I only realized this at the end of my candidature, what my supervisor had told me right at the beginning. A PhD is a training ground to become an independent researcher. It does not sound glamorous, but I think it sets the right expectations and it allows you to focus on developing and honing new skills. I also fell for a common trap of being drawn into a false sense of security of being on top of my stuff, especially when my first experiment resulted in a conference paper, a patent application, and being invited on national radio to talk about my research. Thankfully, I was fortunate to have a supervisor who kept me grounded, but even if he did not, it was the inevitable struggles and failures that followed afterwards that did the job of grounding me. In my opinion, I think I have become a bit more pessimistic as a result, but I think it is always better to maintain a level head, even if things are going really well, because failure could just be around the corner. The other thing I had to get used to was failing along the way. A good example is when I had discovered a major flaw in my experimental setup during my third year, which I had previously not given much thought about. That essentially meant redesigning the experiment and starting again. But in the process, I was forced to learn new things, such as electrical engineering, to solve problems that I never had solved before. And I was lucky enough to have a very supportive co-supervisor, Dr. Toby Boyson, who is a lecturer at UNSW Canberra in electrical engineering, who guided me but did not spoon-feed me the answers. It felt incredibly challenging and frustrating, but in the process of pushing through, I discovered a love for electronics. Lastly, I had to learn to defend my research in the face of outright rejection by experts in the field. I submitted my first journal article on my PhD research to a top plasma-based journal, which was just rejected by the associate editor with a letter that looked a little bit like the one shown here on the right. And yes, even the annotations felt very relatable. And even after, and they had done so based on an assumption which was not necessarily true about my results. Even after providing a good counter argument to their response, the paper was not considered further for publication, with a follow-up response from the journal saying that the panel had decided to go with the decision of the associate editor. Yes, the peer review system is not perfect, as I discovered. So we approached another journal, and again, the article was rejected in the first review, but this time the reviewer had provided a detailed 8-page justification of why they had concerns about my results. As you can imagine, I was on the verge of giving up and settled with the idea of submitting the article to a lower tier journal. I sent an email to Sean explaining to him why we should do so, and he responded to me with one of the longest emails I've ever received from him. It convinced me that it was crucial to not simply give in and accept the decision without an objective look at each of their concerns and criticisms. So in response to their review's 8-page report, I wrote an 18-page rebuttal report, systematically demonstrating with experimental evidence why none of their concerns were an actual issue. To my surprise, the reviewer made a 180-degree flip, having been convinced of my arguments, and eventually accepted my paper for publication. It felt pretty good afterwards, but during the actual process, I wondered a lot if any of this would be worth the time and effort. And it turned out this time that not only was it time well spent to convince the reviewer of the reliability of my data, but all of that extra work had gone into forming the basis of my chapters in my thesis, as well as future publications. This brings me to the final section of my talk and the current phase of my journey, the postdoctoral stint. It was during the final few months leading up to my thesis submission when my supervisor had approached me with a postdoctoral opportunity on a unique project involving scramjets. The position had to be filled up quickly, and I did not have anything lined up after PhD. So literally 2 days after handing in my thesis, I began my first postdoctorate with my supervisor, Sean. It was a 2-year Cooperative Research Centres project, or CRCP, funded by the Australian government and led by private defence-based industry, Defentech, with collaborating partners from academia, government, and industry. The goal of the project is to develop a new liquid hydrocarbon fuel technology for hypersonic air-breathing engines, scramjets, and to support the commercialization of Australian-designed scramjet engines, in addition to investigate advanced ignition technologies for supersonic combustion. Unfortunately, I cannot share any of the details of this project with you as it is highly sensitive and classified. But what I can tell you is that it was a pretty cool project to work on. This brings me to a final bit of my presentation and at the present moment in my journey. How did I end up in JAXA? Having brought to my attention by Sean, I applied for the Japan Society for the Promotion of Science, or Nihon Gakujutsu Shinkokai in Japanese, that was advertised by the Australian Academy of Science in Jan 2019. I did it mainly as a good exercise to apply for grants or fellowships in general because I did not seriously think I would be successful in getting such a highly competitive fellowship. Sean used his extensive network to put me in touch with my now current boss, Professor Hideyuki Tano at JAXA, and he was happy to support me should I succeed in getting the fellowship. With nothing to lose, I submitted my application with glowing recommendations from Sean and my colleagues at UNSW and had completely forgotten about it. A few months later, I received the unexpected email from the Academy informing me that I had been nominated for the JSPS Fellowship. The only thing left was for the JSPS, which is funded by the Japanese government, to accept the Academy's nominations. And well, the rest is history. I commenced my fellowship at the High Enthalpy Shock Tunnel, or HIEST, at the JAXA Kakuda Space Center in Japan last year. A bit about HIEST. It was conceived in the 80s, constructed in the 90s, and finally commissioned in 1998. The facility was a response to the Japanese government's ambition of launching a single stage to orbit space plane called HOPE-X, which is shown here on the right. And it looks a lot like your space shuttle. The large-scale dimensions of this facility were sized based on the requirements needed to investigate the extreme heating that HOPE would experience during re-entry into the Earth's atmosphere. Turns out the mission never went ahead and it was scrapped. But we were left with an amazing facility. Interestingly, the original design proposed by WBM Stocker, of which Professor Ray Stocker was the director, and I'll get to in a bit about who Professor Ray Stocker is. It was a whopping 250-meter long facility. However, due to budget restrictions, the proposal was not accepted, and it was these two gentlemen, Katsuhiro Ito, shown here, and my boss, Dr. Hideyuki Tano, who led the charge to design and develop a facility within the strict budget limits. With a total length of about 87 meters, HIEST is one of the largest free-piston shock tunnels in the world, and for a while it held the record for the largest facility until China built an even bigger one recently. Just to give you a sense of scale, here's me inside the test section of HIEST with the nozzle shown here on the right. I wanted to mention an interesting bit of trivia if you weren't previously aware of it. The free piston shock tunnel is an Australian invention and probably one of the most important contributions, if not the most important contributions to the field of high-speed aerodynamics. It is the brainchild of the late Professor Raymond Stocker, who came up with the idea in the late 60s and successfully executed them in the late 70s to early 80s at the University of Queensland. I'd like to quickly talk about a couple of projects I'm currently involved in. The first project is the one I proposed in my JSPS application, which is the development of a laser-based sensor to make measurements of the free stream or test flow in highest, specifically temperature, density, and velocity measurements. This is important because you need to be sure that the properties of the flow being used to investigate the complex flow physics you're interested in is actually representative of actual flight. However, due to COVID, which affected everyone, it also affected the original schedule of these experiments, which was meant to happen between July and August of this year. It will now happen, hopefully, sometime early next month. Shown here on the left is my design concept of the experiment, for the experiment, and to the right is the actual design that I plan to use for the experiments. I'm happy to take questions about these later if anyone has any. And finally, the second project I'm currently involved in has to do with characterizing the instabilities found within a transitional hypersonic boundary layer. The technique is a laser interferometry-based technique called focused laser differential interferometry. Having never done this before, I put my hand to give it a shot, and if successful, would be the first in highest. Thankfully, I'm not completely alone on this project, with researchers from Tsukuba University who arrived recently and who have some experience using this technique, of setting up this technique, who will give me a hand to set it up at highest. And with that, ladies and gentlemen, I'd like to end by saying that although my journey into aerospace research and my path to JAXA has been challenging, it remains one of the most rewarding things I've done. With the right support, determination, and perseverance, and a bit of luck, I believe that this should be sufficient for anyone to boldly chase after their dreams. Thank you, and arigatou gozaimasu. Happy to take any questions.
Thank you so much, Rounak, for your lovely talk. That was really, really well done. All that training in public speaking is showing.
Thank you.
No, that was excellent. Thanks. We do have a couple of questions. You mentioned career plans, D, C, E, F, and the rest of the alphabet.
All right.
So, what were those career plans, and how come they were D, C, E, F, and not before that?
So, like I said, back then, back then I was. My goal was to become a mission specialist astronaut, but I knew how difficult it is to become one. And so to avoid disappointment and just being left with without any other alternative, I made sure that I thought about other things as well. So other alternative career options, which was still in line with aerospace engineering and space exploration. So one of them was to become a researcher at NASA JPL, and it still is my ambition. Then another one was to become a scientist at a leading university or research institution, or a physics teacher or a maths teacher at high school, because I enjoy teaching and I enjoy maths and science. And I also had music teacher for a while because I really enjoy music, and that's my after aerospace engineering, I guess that would be my passion and my hobby. And so I did consider becoming a music teacher too as part of the options, but I knew that was very unlikely to happen. So those were my B, C, D, E, F plans, so like I mentioned.
That's a very diverse interest.
Yes.
Ranjana actually asked a good question from a layperson. What is hypersonics? Where does it start and where does it end?
Right. Well, so I mentioned very briefly that hypersonics is a flow regime. So you start with flow that is lower than the speed of sound, then you reach the speed of sound, and then you become supersonic. And then when you go past 5 times the speed of sound, that's when your hypersonic regime begins. And it's 5 times the speed of sound to whatever limit. So Mach 25 is what a space shuttle would experience when it's re-entering the Earth's atmosphere, for example, I think. But it's anything above Mach 5.
Thanks. And Dawson Dawson is asking, how long does it take to set up for a shot at the heist facility, and how long does the shot itself last? Are multiple experiments run concurrently during each shot?
That's a good question. As Dawson is probably aware, at TADFA, you could probably run 5 shots a day, but here at Highest, you can get 1 shot done realistically, maybe 2. And it takes between, say, 9:30 to about 12 o'clock to set up the shot, so about 2 to 3 hours. And the shot actually lasts for a fraction of a second. And usually there's 1, maybe 2 experiments. I shouldn't say experiments. There's 1 experiment, but maybe more than 1 diagnostic technique being used to investigate the flow field.
Thanks. And Sneha is asking, I just wanted to ask, what developments in industry are you most excited for? What do you expect to be one of the biggest developments in aerospace over the next 10 years, whether it be things you're working on directly or indirectly?
That's a good question. I think one of the developments, at least I think in Australia for sure, is the whole university-based CubeSats, small satellites, and I'm really interested in those things. And I think in the next 10 years or so, that's going to be, it's already is, but it's going to get even bigger. And with the Australian government investing a lot of money in its new space industry, that is something I'll be keeping my eye on. And for me personally, I think it's also what I'm really interested about CubeSats is about station keeping, about using plasma thrusters for station keeping. So, and there are a lot of startup companies. I can think of one in Australia, Neumann Space, who are developing these small plasma thrusters for small satellites. I believe there's going to be one launched next year with one of the Neumann Space plasma thrusters on it.
Thanks. I actually have a question about CubeSats. Are you doing swarms of CubeSats, and how big, if you're looking into swarms, how big would those swarms be? Would it be centralized, like a centralized control, or individual control?
So I'm not well aware about satellite swarms. I guess my interest in CubeSats is about the station keeping aspect where you use small thrusters to maintain the orbit. So I'm interested specifically in the plasma thrusters that are used and will be used on these CubeSats, and that's because I have a background in plasmas, and it's what I'm interested in. So I'm sorry, I'm not sure I can answer that question.
Fine.
Yeah,
that's fine.
Yeah.
Vani says, great presentation. Do you think COVID has caused any hindrance, delay for the aerospace industry, or is it business as usual for you guys?
Oh, it's definitely caused disruptions, I think, everywhere, including the aerospace industry. And while I'm not well aware of individual companies, I can speak to the fact that JAXA had shut down for an entire month in May this year. And that basically meant postponing everything to later this year. So I'm sure that has had similar effects all over the world in the aerospace industry with delays and so on.
All right. Any more questions, please keep sending them. We're getting some really good questions here. What about working and living in Japan? Japan is notorious for getting visas. It's hard to get visas. So how hard was it for you to actually get a visa to live and work in Japan?
In my experience, it wasn't hard. And I think that's probably because I was awarded this fellowship. And so it was simply a matter of presenting to the embassy that the reasons for my travel, and it was supported by JAXA and my boss. And so it was a pretty straightforward process. And fortunately, we didn't have any issues in getting visas.
How long did it take from when you put the application in
to when we got it? Right.
Yeah.
I think it was about a month and a half or 2 months until we got it. Funnily enough, when we did apply for the visa, I was in Sri Lanka, in my wife's hometown. And so we we applied for the Japanese visa while we were in Sri Lanka at the Japanese embassy.
Okay. Right, Prachi is asking a great presentation. Can you please guide us how to approach people who are already working in this field? Being new in the field, it feels like lost sometimes.
How do we guide people in this field? I'm not quite sure.
How to approach, not how to guide, but guide people that are new into the field, how to approach people already in the field. Prachi, good start would be joining AIAA. If you have AIAA to where you are, because that's where aerospace professionals join. Rounak, anywhere else?
Yeah, get involved in university-based clubs that, you know, do aerospace-related projects. I think it's important to partner with like-minded people, and you will find that some people are able to give you direction and guidance, people who have more experience than you. So if you were, for example, for me, the AIAA Sydney section was a great opportunity to work with more senior researchers and academics who were able to mentor me and guide me. So that's a good way to get, especially young people who are starting off, which is what I think you're referring to here, who are just starting off in the field, to provide a sense of direction.
All right, technical question, Jeremy. Roughly how much data would you computationally or otherwise capture for each shot of the heist facility?
Right. I think the maximum we have is 104,000 samples for a single measure, say a pressure measurement. Yeah.
All right, and Spanner is asking, have you observed any cultural differences in approaches to problem solving and engineering solutions between the engineers working in JAXA and other countries that you have studied and worked in?
Right. Unfortunately, I can't give you a very in-depth answer to this, but in my limited experience here in Japan, and from what I've observed, whenever there's a problem to be solved, the team comes together and there's a discussion about it, which I don't think is very dissimilar to what happens most places, even in my experience working in Germany. But because of the language barrier, it's hard to pick up on nuances in the way they approach the problem. And so, which is why I can't really tell you if there are any very distinct differences in the way the Japanese approach problem solving to, say, people in the Western world.
Thanks. Any other questions? We've got probably time. Oh, a few questions. Hi, Rounak. Again, thank you sharing all of that. What has been sorry, Anton, I'm not going to read the whole question. Rounak can read it later, but I will pass the question. What's been the 3 top personal takeaways for you in this challenging and rewarding journey besides meeting the love of your life?
All right. Was that Anton?
Yes.
Thank you, Anton. Thank you for the question. I think after reflecting, and it required me to reflect a lot for this talk, I think the one main thing is just sheer perseverance and being absolutely tenacious in solving a given problem. I think just being experienced with so many new problems and trying to solve them, you have to remain perseverant. So I think being persevering is one of the key attributes to have in approaching new problems. I think patience as well, because it's very easy to get frustrated and then give up. And believe me, I had many moments during my PhD and my postdoc where it was really frustrating, and the easier option was to give up. So remaining patient. And the third one is to just kind of remind yourself that it is just research after all, and that there's other things to life, and not to be so caught up in it and forget to live life. So I think putting things within context for me has been a very important lesson that I learned during my time.
So Pablo's asking, what is your advice for current aerospace engineers?
So I'd say so one of the things that I wish I did better probably in my aerospace degree would be if it would have been to engage with university clubs that did extracurricular activities and actual engineering projects, not just working on your assignments and your tests and exams, and that's it. And for me, I only focused on those things, and I focused on wanting to get high distinctions. And yes, it's good to get high distinctions, but I think what's probably more worthwhile is spending more time trying to understand a complex concept or a principle. And one way to do so is to solve more problems, find new problems online or in a textbook. And I'm not just talking about theoretical problems. I'm talking about problems that you can build, you can test and verify. And I think in doing so, you develop a more intuitive sense for physical problems that go beyond just solving complex equations. So find opportunities to engage in such opportunities, engage in such engineering work, join clubs that, like the AIAA, that will give you opportunities for other things like this one, like giving presentations, talk about your research. And you'll also find that you get to meet a lot of interesting people, and people who probably would help you later on in your life, in your career and otherwise. So I think those would be the two main things I would advise new aerospace undergrads.
Hi, thanks. Dawson has another question regarding the language barrier. Does this also affect software scripts and code, and how do you manage that if they're in Japanese?
Google Translate. Thankfully, all of the code is written in English, so it's either MATLAB or Python. And the only thing that's in Japanese are the annotations and the notes that they make, but I simply copy and paste into Google Translate, and for most of the time it works.
Lisa, I'll leave the personal parts out and just ask the question.
Sounds good.
Rounak will stay online after, and then he can read all the comments. So Lisa's asking, do you read novels for enjoyment, or is just science for you?
That, by the way, just to let everyone know, Lisa was my English teacher in high school, so that's a very apt question to be asking, Ms. Glanville. I can't remember when I last read a novel. I think the last book that I read, or at least got through the first few pages, was The Intelligent Investor by Benjamin Graham, I think is his name. Yeah. And the one before that was A Brief History of Time by Stephen Hawking. So they're not fictional novels, they're science-based, non-fictional stuff.
So, Ms. Granville, he still does not read normal novels.
Yeah.
So another question from Xiong Yang On. Do you recommend aerospace engineer to go through the postgraduate education?
It really depends on, well, okay, so postgraduate is a big term because it could include research or coursework. Now, if you feel that doing a master's in coursework would improve your odds of getting the job you want, then yes, you should definitely do that. But if you're interested in research, then master's by research, or in Australia, you can jump from undergrad to PhD directly. So I would very cautiously recommend someone who's considering doing a PhD, because you should only do so with the right motivations, and if you're really passionate about research. And if what you're really doing is to improve your odds of working in industry, then you don't really need to have a PhD to work in industry. So it really comes down to that. It comes down to your motivations. Are you research oriented, or you're simply qualifications oriented, I guess, for the lack of a better word.
And Nimish is asking, as a person who has worked in a multicultural workplace like the DLR, JAXA, which enjoy global and national collaboration, what would be the common traits that Australians can learn from your experience? Kanban, agile method of work, anything else?
Sorry, I didn't get the last part.
So what can Australians learn from your experience in terms of agile methods of working in general?
What can Australians learn?
From your experience, as in, don't be blunt, you know.
Right. I understand. Okay, thank you. Right. I think it's important to read the room, and I think that's true just generally in life. I don't think there is a way to act in a different culture. I think you read the room, you do some homework, you try to study about the culture you're about to work in, and then just try to apply the same sort of approach and behavior that your fellow workmates seem to be doing. And for me, that's exactly how I did it, because even though I've lived in Australia for a long time now, and I'm an Australian citizen, I grew up in India with I guess, Asian values, which are very similar to the Japanese values. And so that has been a huge advantage for me personally. But I think doing a bit of homework and just educating yourself goes a long way before you go into a new culture. I think that's personally what I think that makes sense.
Right. I'll got time. We're over time, but we'll do two last questions. There's quite a few of them. What advantage have Australia, Germany, and Japan? What advantages have Australia, Germany, and Japan different from each other in the aerospace context?
Right. Well, I'm not too sure. I don't know if I can answer that very well, but other than saying that Japan has the largest ground testing facility in the world, and so that's, I guess, one advantage in hypersonics research. I guess if you're in Germany, you're on a more central location, and you have the opportunity to work with the neighboring countries as well. So I think the advantage there is more job opportunities compared to, say, if you were in Japan. But that's just my guess. I'm not entirely sure. So I'm not sure if I can answer that really well.
Last question for the evening. What advice would you give to mechatronics physics student trying to break into aerospace sector besides joining societies and AIAA? Question is from Ashnith. I'm sorry if I mispronounced your name.
Okay, that's a good question. Actually, so Australia does a lot of space-based mechatronics. I think there's the Australian Centre for Field Robotics in Sydney that does a lot of work related to rovers. So if you're interested in planetary exploration, like the Mars rovers, then I would strongly recommend you looking into that as an option. And that could lead to further opportunities. I've got friends who started there now working for JPL on Mars, on future Mars rovers. So that's what I'd recommend. So there are opportunities. If you're from Australia, that's what I would suggest you do, is to look into the Australian Centre for Field Robotics as one example, if you're interested in getting into the space domain.
All right. I think we'll wrap up for this last question. Thank you so much, Rounak. That was absolutely wonderful talk.
Thank you.
The AIAA committee members from Sydney and Canberra and Adelaide, you can stay online. We'll follow through so Rounak can read all the comments. Rounak, sorry. You can read all the comments. And to the rest of you, good night if you're on this side of the world, and good day to anyone else.
Bye.
See you later.
Excellent presentation, Rounak.
Thank you so much.
Well done.
Thank you.
Well done.
Thank you very much.
Beautiful, Sana.